Are we recording?
Enter.
Hello. Welcome to Stringer's Clubhouse. I am your host, Dragonborn, and in this episode, I'm going to be continuing my series on the 4 fundamental forces of the universe. In my first 2 episodes, I covered electromagnetism. Part 1, electrostatics. Part 2, magnetism. But this part 3, I'm going to move on to possibly the one we're most familiar with, but also the most mysterious of them all. Gravity. It's the force that makes things fall to the Earth at 9.8 meters per second. It's the thing that keeps the Earth in orbit 93 million miles away from the Sun. This is not an accurate representation, or this is the equivalent of 1 astronomical unit. So, if you hear any astronomers talk about something being 3 astronomical units away, this is what they mean. And this is how fast the Earth orbits. It's kind of erased, but if it wasn't erased, it would read 30 kilometers per second. And it's also one of the things that causes our galaxy to move at 1.3 million miles per hour. So what is it? Well, we're probably already familiar with it, but if we're not, it's essentially the attraction between 2 bodies of either energy or mass. I need to make that distinction, and I have to talk about 2 things first before I get into this any further. E equals mc squared. You probably heard this equation before, probably been able to figure out E equals energy and m equals mass. C equals divided by the speed of light cube squared. And the main thing that this states is that energy and mass are essentially the same thing. So if there's anything that's mass, that something with mass can do, something with energy can do it as well. That's important to state. I have to make that important first. I have to say that first because in more classical physics, like Newtonian physics, gravity is oftentimes measured by the force equals mass times acceleration. But mass and energy are the same thing, so you can replace mass with energy. This explains why photons are still affected by the gravitational pull and can have a gravitational pull of their own, even though they are massless. And I should mention the speed of light is the speed of massless particles. It's just light was the first massless particle for us that we discovered, and the name has stuck. Second thing, space-time. So this is, at the most basic level, the relation between space and time, how you can't really distort one, or you can't really affect or travel through space without somehow affecting your own time. More on that later. And oftentimes it's represented as a grid. Sort of, this is just I'm not very good at drawing, but imagine a grid. There are 2 main representations of gravity, of space-time rather, as a flat sheet. Like, for instance, if this Enderman, yes, I don't play Minecraft anymore, but I used to play Minecraft, and the Enderman was my favorite mob. Anyway, well, I'm a nerd. My director is laughing at me. Sorry. Anyway, so let's say the mass in this Enderman plushie has an, and let's say there's one of the first representations that you probably already think of is space-time as a flat sheet. And if you would imagine like a flat sheet, and then this Enderman, when you drop it on the flat sheet, would actually curve it. This is one interpretation of how gravity works. But the other interpretation of what space-time actually is oftentimes a 3-dimensional grid. While oftentimes in more advanced physics, they'll actually show that shows space more as a three-dimensional grid, but oftentimes the two-dimensional space is just to give you an idea. Now, as I mentioned, that's the current. Now, there are multiple ways to interpret how gravitational force works. The first one, well, there's been several over the millennia. The first one was that it essentially was the will of whichever god you believed in. We even moved away from that to a more classical physical interpretation, in which gravity is a force just like electromagnetism, just with the properties I'm going to mention. And our current explanation is, as I mentioned, that curvature of space-time, that things with mass or energy actually curve the space-time around it. So if you would imagine like walking on like a sidewalk, you can continue to try to go in a straight line, but you can't go in a straight line even though you think you are. But you are actually going in a circle, not because you're trying to go in a circle, but because the path you have to move on is actually going in a circle and changing. That is our most current description of the gravitational force. So, what is the gravitational force, and what are its properties? Well, as I mentioned, it's the attractive force between two bodies with mass and or energy. So, sorry, Stash. So technically, everything has a gravitational field, including this Enderman plushie or my cat Stash. If gravity was as strong as electromagnetism, they would fly right toward each other. But the gravitational force is actually the weakest of all the four fundamental forces. Here's the list from strongest to weakest. The strong nuclear force, electromagnetism, part 1 and 2 in this series. The weak nuclear force, and gravity. But one of the things that sets gravity apart is that it technically has an infinite range. It's just when you start getting out to these infinite ranges, the gravitational effect is so small that you pretty much can't detect it. Or, like, for instance, if you were sitting in space by yourself, and then there's a galaxy far away, like billions of light years away, or millions, it might take you longer than like 3 times the expected lifetime of the universe for that gravitational effect to draw you to that galaxy. It's still there, it's just so small that it's pretty much negligible. So, other properties of gravity are there's no repulsive force of gravitational pull, as far as we know now, with our current detection. So you will not see two things that, although there is a kind of a theory about how the Big Bang started, that gravity actually acted as a repulsive force and spread the entire Big Bang out, but I'm not going to get into that here. That's too complicated to explain in this video right now. Instead, those are the basics of gravity. I'll move on to how it affects light and why we've come to interpret the way Albert Einstein interpreted it as correct. We have actually done multiple experiments to actually prove this, and one of the things that it predicts is because of the curvature of space-time, it would also affect light. So essentially, if there's a light beam heading there's maybe a star here, the Earth is here, and a star 4.4 light years away. Its light is coming this way. However, if the sun is in front of it, from our point of view, if space-time wasn't curved, then it would simply just be blocked and we wouldn't see the star. However, that's not what we see. What we do see is we actually have noticed that the light actually curves around the sun, so we actually see it in a point in the sky where it actually isn't. onto the whole mass and energy thing, I'm going to talk about. I know I'm approaching going beyond 10 minutes, so the last thing I'll mention is black holes. Very simply, a black hole is a point in space in which there's something there with gravitational pull that's so strong that not even light or any massless particle can't escape. That's why we call them black holes, because no light can get out of the event horizon. That's essentially the point of no return for a black hole, and thus we cannot get any light from there to see what's in it, and you get the idea. But there's actually two different names for a black hole formed by mass, like for instance a supermassive star's core, after when the star goes supernova and the core collapses into a black hole. And there's also a black hole formed by energy. It's been speculated that maybe in the far future we might be able to actually use a very high-powered laser to form a black hole from energy. It's hypothetical now, but it's theoretically plausible. And a black hole formed by energy is actually called a Kugelblitz. And where I actually learned this, it was an episode on temperature in general, and that essentially the more energies that the closer you get to being the more energy something has, the closer to becoming a Kugelblitz something becomes. Kind of like the Schwarz. It's a way to work around the Schwarzschild radius. Instead of crushing this Enderman plushie so much that it becomes a black hole, instead I could just heat it up so much that it has enough energy to become a black hole. And also, one thing that's very important to black holes, as we know them today, is Hawking radiation. So, not even black holes last forever. Why? Because of Hawking radiation. This is actually related to my virtual particle episode that I did earlier. Subscribe to the channel and check that out. And how this works is that basically outside of an event horizon, there's actually particles, the virtual particles that the sheer amount of energy from the black hole actually pops into existence. And the idea is that oftentimes these particle pairs might be entangled. One might be a positron, one might be an electron. The idea is that one might fall into the black hole, thus the other one becoming a real particle, and if it has enough energy, escapes the black hole. In other words, stealing some of the black hole's energy for itself. While black holes can last for hundreds of trillions of years, eventually this Hawking radiation is going to suck it dry, depending on how massive the black hole is. If you're talking about a black hole, if you're talking about a small black hole, it might last maybe 5 years if it doesn't suck up any more mass or energy. But I'm going to get into something that's been speculated, that's people have been worrying about. The CERN particle accelerator creating a black hole. Even if it does create a black hole, it's going to be called it's called like it's called a micro black hole, and there's so little mass and energy within that black hole that it will dissipate almost immediately. So, for anyone who has that worry, you don't have to worry about that. So that's going to conclude our episode on gravity. I hope you actually enjoy. I hope you enjoyed this video, and if you like this kind of content, like and subscribe to the channel. I have more science videos up for you to watch. If you have any questions, comments, or suggestions on videos I should do, put them in the comments below. Put in the comments below also which of the other two fundamental forces I have left to cover do you want next: the strong nuclear force or the weak nuclear force. I hope you have a good night or day, whatever it is. It's night here, and let the science be with you.